Thanks, Jim. Yeah, I've been to many OFA workshops. I think my first one was in Sonoma in 2000 and some single-digit number, I forget exactly. Anyway, I spoke about this very topic a couple of years ago, so this may be familiar. And I'm going to skip over some of the introductory material. I hope that's not frustrating to some folks, but you know, we've talked about it before, and in theory I have a half an hour, so I'm going to talk about the future rather than catch people up. But my approach is a top-down discussion. I've been doing this work bottom-up. I've been approaching from the RDMA direction, but I've also been working from the top. As Jim mentioned, I'm an active participant in the SNIA non-volatile memory programming model, the so-called NVMPM. NVM is a bit of a historical artifact, but we still call it by that name. That's a high-level abstract API that I'm going to describe. And I'm going to use that as motivation to drive down the stack. And I think the farther down I go, the more interesting it'll be to you, but forgive me while I start at the top and move down. So at the end, there are some next steps. All right, so the SNIA non-volatile memory programming model is currently at version 1.2. 1.2 was actually published in 2017. We've been working on it, but fundamentally, it's there to expose these so-called new block and file features to applications. This was embarked on about 4 years ago, a substantial length of time ago. It produced a couple of early drafts, and this 2017 is actually not bad, but it's a local programming interface. It's not a concrete API, it's an abstract API. It's sort of an architecture and an object model for creating persistent memory applications. And in addition, the SNIA has gone through many of the implementation questions, the sort of the error cases, the semantics, the mapping, all the little, the difficult corners of the question. It seems really simple at first. You say map and sync. Okay, I map the file, I write the memory, I sync the memory. It's not that simple, and SNIA has spent a long time looking at this. So if you haven't looked at it, you'll probably be interested. Like I say, it's not a concrete API, it's describing a high-level approach. There's a second effort that the non-volatile memory programming twig has been working on called remote access for HA. This was taken up a couple of years ago. There was, the first white paper was published in 2016. It was just, you can ignore it, frankly. It was enhanced and published in just last month for public review, this so-called 1.1. The twig has been working on this for the last couple of years. I've been contributing to it heavily. It's basically a mapping of the NVM programming model to an RDMA provider. I'll show a little more detail on the next slide. But while doing that, we realized that the original programming model was actually rather limited in terms of its richness, in terms of its ability to apply here. So it's been extended. We've updated the specification in the HA model to imagine these new operations. We haven't published the updated specification yet, though. So in parallel with the remote access for HA, we are updating the NVM programming model to 1.3. You might actually see these two documents merge. Although there is a bunch of stuff in the remote access for HA that's not about programming models. It's about recovery scenarios and applications and things like that that are probably best kept in a separate document. But you're going to see all this stuff appear in NVMP 1.3, I believe. And finally, the output of the remote access for HA review, we hope, is a collaboration with OFIWIG. We have an agreement, a sort of a standards agreement between the two groups, OFIWIG and SNIA. It covers intellectual policy, it covers contributions in both directions, and we have basically an open dialogue prepared We're waiting to have it in detail. We've received some comments already from OFIWIG, thanks very much. But we expect this to be a partnership. Right now, what we SNIA, I'm going to put my SNIA hat on and say that we hope OFIWIG will provide expanded remote access use cases. The sort of, how would an application use this? What sort of workload will flow over this? Why do you want to do it? Let's draw the value proposition at a high level. But in particular, we want to get down and dirty. We want to talk about, how RDMA applies in great detail, and how, for instance, OpenFabrics libraries could implement some of this stuff. And you'll see that that's where this talk proceeds to go. Now, maybe I'm leading you down that path. I don't know. So here's the basic idea that SNIA began with for the remote access for HA. Persistent memory modes by adding remote. So the stuff on the left-hand side of this picture is basically the SNIA NVM programming model. A little bit simplified. We usually draw a more complex diagram. But you can see that a program, that a persistent memory aware app up at the top can go through one of two layers, the file mode or block mode, volume it's called here, to get to a PM device. These are, if you will, legacy APIs. This is the file and block, the raw device sort of APIs. The file system can use those APIs in kernel. This is not shown, but the application can actually use these APIs out of kernel. And these are implemented on operating systems today, and they're extended with file systems such as DACs and emulations, block emulations, which are basically RAM disks, right, that happen to reside on persistent memory. So all that stuff on the left is already well established. We understand rather well what the local programming interfaces are, and major OSs like Windows and Linux support everything you see on the left. They've done that for several years now. On the right is what we're adding, and that shows these two RDMA NICs that kind of hang outside the programming model box, but have arrows leading up to it. And so an extended programming model that is RDMA aware, we view being able to operate over an RDMA NIC to a remote machine that has possibly nothing but persistent memory in it, right? There's a CPU there, obviously. There's a NIC there, obviously. But we're not going to invoke that stuff. We're just going to use the NIC to do RDMA. There's actually no software required on the other side in this model. Now, if there is software, there's lots more stuff that'll happen. Of course, there will be software. There'll be upper layers. I'll talk about that. But this is, if you will, the most simplified model, where you have PM over there on the right and the SNIA programming model over there on the left. So the remote access for HA that would use this sort of infrastructure is developed by the NVM programming twig. It's an interface specifically for remote persistent memory. The remote access for HA document talks only about the remote case. It makes changes to the local case or recommends changes, but it doesn't modify it in any meaningful way. We did that on purpose to maximize the alignment with that local PM interface, right? This picture on the left, we don't want to change that box on the left any more than necessary, just those little arrows emerging from it, right? So we examined how lightly can we touch it? What do we need from that box to do it? Taking the remote environment into account, what's actually there, right? RDMA has features, limited number of them, and it has restrictions, right? There are certain ways that you use RDMA that it doesn't behave like a local memory DMA channel. And in particular, we were going to analyze the error cases. As always, this turns out to be the hard part, the really hard part. In fact, that's definitely the hardest part of doing the NVMP interface. The success case is great. Everything is great. Nobody has any problem with the success case. But the errors are really awful. You touch a byte, and all of a sudden you realize that it's not just a bad byte. It's a whole page. It's a whole cache line. It's a whole bunch of other bytes. We call this the blast radius, right? Something bad happened here, but it damaged stuff not far around it. With block devices, you have sector atomicity. You know the block is bad, but you know that only the block is bad, right? That's not the case with PM. So now we have a network in the way, right? It gets even worse. So we've spent a long time on that one. We believe that the remote access for HA specification that we have today is directly mappable to RDMA, possibly with extensions. There are extensions within the local programming model for efficiency primarily, and there may be extensions for the RDMA, which is the subject of my talk. In NVM Programming 1.2, the version that's out there published today, we have these things called optimized flush and optimized flush and verify. And I'll talk in a little detail about why they were awkward on remote. We have added something called async flush and async drain, which are components of the optimized flush operation. We've separated them. And we've also specified an ordering primitive, a way that you know that it was your writes that got flushed. You know, that if the writes preceded the flush, that the flush acted on them. And this is important because at the programming layer, you need some sort of way to order your operations. They all need to go through some funnel in order, right? And that funnel is an object in your programming paradigm that you need to really understand well. So that's what we're trying to bring out in the NVM programming model. And there are some other NVM programming programming model methods, which we believe are remotable. However, we're mostly leaving those to the upper layers, and we talk about those when we do. Okay, asynchronous flush is the new feature that we've added to the SNIA NVM programming model. This is not yet published. We have documents that are in development in SNIA. They're visible at this time only to SNIA members, unfortunately. We are sharing some of them with OFIWIG, so if you're participating in OFIWIG, you may have seen some of these. But we are in the process right now, actively, this calendar year, updating that spec. So these will be available in published version not long from now. They're not really a secret, but the process requires us to manage the information in a certain way. So optimized flush works by both pushing writes, flushing the pipeline, if you will, and performing an actual flush to persistent memory, right? The word optimized in optimized flush was intended to mean that it could bypass the kernel. It could be invoked from a user application. It was effectively CL flush opt, followed by, well, it was the old pcommit instruction, but in effect, CL flush out plus sfence in the Intel lexicon, which were user high ring application instructions that you could invoke and manage persistent memory. And it's all great. The problem is that optimized flush specified them both in one operation. Right? You would both push the data toward PM and commit the data or make sure the data had reached PM. So it was synchronous. It would basically always wait for the completion of the write and the flush. And it's fairly expensive, even though it's, quote, optimized. It's cheaper than going to the kernel and saying, I don't know what I'm doing. Can you flush the stuff that I might have dirtied, please? And the kernel goes off and finds dirty pages and flushes dirty pages and all that stuff. We don't need to do that with optimized flush. We can just say, here's the memory, go flush it. That's not so much of a problem with local applications because they got to do all that work anyway, and they call optimized flush. It takes a little while, it finishes, they're done, right? When you put a network in the middle, it's a very different picture. The stores on the local machine, for instance, just went to memory. So now we got to push them across the network. You know, how do we know when to push them over the network? We're not going to take faults and push them every time the user touches a cache line, right? We're going to buffer them up, and we're going to wait for the user to tell us he's ready to push it. That's really late. Let's say the user wrote a gigabyte of memory, and then he calls flush. Well, all of a sudden, we got to wait for a gigabyte to transfer before we can satisfy the flush. So the RDMA latencies, the latency of actually sending the data, is much higher than local, right? Local, you have a few hundred nanoseconds or maybe less, depending on your architecture. RDMA, you've got microseconds, order of magnitude at least. So it magnifies the impact of the optimized flush pipeline. So our solution was to separate the two phases into an async flush, which does a write, and an async drain, which does a flush. I know the language is a little odd, but you know, if we'd thought this through when we started, we wouldn't have chosen the wrong terms. Maybe we'll fix this when we publish it. And we need to introduce this ordering nexus, the barrier operation, that says when I call flush, everything I wrote before that is flushed, right? That's called a barrier. And we want to make sure that the writes have been pushed before the flush takes effect. So we try to get off our platform knowledge, or try to get up out of the cellar and get up to a sufficiently abstract layer that we can define these things. And we feel we have, and I'd love to see it. I'd love to see your comments. It allows the overlap and parallel processing. In particular, it makes best use of the network by allowing the application to push early. The application can call flush anytime it wants. I wrote a few bytes flush. I'm definitely going to commit exactly those bytes, so you might as well move them. I'm not going to overwrite them. So move them. I got a little more work to do. I'll tell you to flush real soon. We call it giddy up because we basically say, giddy up, we loaded you up, giddy up, get off on the network and move over there. It lowers the latency of the eventual flush by doing that. And, it basically, there's less data remaining locally and less data remaining remotely as well because flushes occur just naturally, right? Caches are evicted. The error cases between flush and drain, though, do require some very careful analysis. Because when you flush, you may have started to write that remote persistent memory. If you don't get to call the drain, that data is in a very uncertain state. It may be committed remotely, it may not. So we have to think through the error case. This is exactly the same problem we have locally, but it's, like I say, magnified by the presence of the network. One other thing that has come up and is becoming increasingly important is the question of persistence versus visibility. Previously, in Intel hardware, persistence and visibility kind of meant the same thing, right? That if it was present in memory, it was present in cache. If it was present in cache, then it was had a consistent view across the motherboard, right? So making something visible and flushing it to persistence were kind of one and the same, basically. They're not. A lot of architectures, particularly high-scale motherboards or non-Intel architectures, don't have that same sort of thing. And they have an additional problem that we call global observability, which is something which is definitely a problem on high-scale motherboards, right? When you shoot down your own cache, you may not be shooting down the cache of another device. And it may be very expensive to reach across the bus and do that. So global observability, we're trying to settle on a new term other than simple visibility, is a new concept and something which we believe that the application needs to be aware of. The reason being that visibility does not necessarily imply persistence any longer on such a machine, right? You could have a volatile cache in front of persistence, right? And the persistence may not actually be mirrored in a consistent way. The cache might be. So it's visible but not persistent because it's sitting in the wrong buffer. Likewise, persistence may not imply visibility. You may have a multi-socket or multi-port architecture and you haven't invalidated all the caches or refreshed all the data. So it might be an inconsistent view. Applications are wise to this these days. The good ones are, and for efficiency's sake, they want to behave differently depending on the type of workload that they support. A storage workload almost always wants to make the data persistent first, right? It can handle the visibility on its own, right? File systems are used to saying, I got a cached copy and it's not correct any longer because the attributes just changed. So storage understands visibility problems really well, but wants that stuff stored, right? So that's its first priority. On the other hand, a network shared memory application may have the reverse, right? A network shared memory may prioritize sharing of this data, of this volatile data, and wants to persist it only occasionally when someone calls some magic, key value API that says, commit this as a transaction. So applications are getting smart about this, and they're saying, which flavor they want, and it may make quite a difference in performance for them to do so. Even if they request both, however, we warn applications in SNIA, persistence and visibility are not reached atomically, right? If you do a compare and swap in quote, persistent memory, trust me, it didn't do what you thought. You may have compared and swapped based on the cache, but you haven't persisted it. And by the time you persist it, something else might happen to that memory. So that lack of atomicity between persistence and visibility domains is really important to an application. Really important. And we're trying to put this in big bright red letters in our discussion. Okay? So we're considering exposing this distinction in the programming model by having a flush type modifier. Right? I want this to flush to persistence, so I want this to flush to visibility. And as a result, the RDMA protocol is thinking about it as well. Under development for the future is also the scope of the flush, this conceptual store barrier. What's actually getting flushed when I call flush? Streams of stores, this is along the lines of the ordering nexus, right? Let's say I have two applications that are sharing a hunk of PMEM. And one of them is flushing at one time and one of them is flushing at another time. I don't want one to be saddled with the responsibility of the other's data. Flush hints, we have this thing called deep flush. That's probably just a detail right now. But we're modeling them in the programming interface in the new version with an eye toward how they're also supported by the protocol. So you'll see some of that thinking in the next section. We've decided on the notion of consumers of visibility versus consumers of persistence. And the failure semantic varies between the two. So that's roughly what I talked about a minute ago with storage versus shared memory. Those are two use cases, if you will, of persistence. And insurance of persistence integrity is another interesting problem. If you don't have a CPU, if you don't have a file system, how do you know the data's good, right? The memory said he flushed it, but how do I know that? And what if an NMI went off on the other node because something bad happened? How do I get that when I'm on the other side of the network? So those sorts of questions are on our mind in the SNIA non-volatile memory. All right, enough motivation. Remote persistent memory is the next phase of the discussion. So I mentioned these before. I'll just list them here as 3 possible persistent memory workloads. The first that the SNIA has looked at mostly is high availability. This includes a number of topics. High availability means a lot of different things to a lot of different people. But resilience, recovery, RAID-like properties, mirroring, things like that. Replication, that's the RAID-like property. Scale out, the ability to add devices and scale the capacity, performance, whatever you need, that sort of question. Those are all high availability questions that the SNIA, by the way, stands for Storage Networking Industry Association. So we understand that type of thing very well in our charter. A second type of workload is transactions, and their atomicity, the presence of a fundamental atomic operation that we can invoke remotely becomes very important. The second question of failure atomicity, if the atomic request fails, what are the boundaries of its failure, right? And how can we recover from other failures using atomic operations? Closely related to HA, but really not the same thing. So we separate them. And network shared memory, including a pub-sub, publish-subscribe sort of model. This is, as I say, a very different workload from a storage workload, but a very real one for persistent memory. Particularly if you have a large array of network shared memory, PM is really convenient because it comes back real quick when it reboots, right? And there are others, and that's what I mentioned earlier. We hope that the OFIWIG will help us identify some of those other use cases. For all these use cases, we desire to maintain the ultra-low latency capabilities of local persistent memory, right? We expect to add at least a round trip, which will give us, speed of light sort of addition. But we want to avoid pipeline bubbles, which may add to that. We want single-digit microsecond operations here. We believe that we've modeled it, and we believe that's quite possible, and with care, certainly achievable. We also hope to have a compatibility between the local and remote programming models. Ideally, full transparency. But we may not saddle everyone with full transparency, because if you really don't need network, you just want to do local, well, maybe there's more efficient ways to do it. The programming model, the NVM programming model from SNIA, is very high level and abstract. So it's very easy to implement it in different ways. We hope that you could implement it with remote or local. and both. So what do we have to do to the RDMA protocol to support these new NVMPM semantics? The first is this animal that I first talked about here over 2 years ago, called the RDMA flush. We've been working on it since 2016. I think I actually mentioned it in 2016 in the OpenFabrics Spring Workshop. It really doesn't feel like 3 years ago. Let me call it 2 years ago. RDMA flush, it was called RDMA commit at the time and still is in my head, is a new RDMA transport operation. It's an existing, it's a new operation, but it preserves the behavior of existing operations. It augments the RDMA language, if you will, by adding a flush operation. It doesn't change RDMA. It doesn't change RDMA write in particular. It doesn't alter the behavior of RDMA read, RDMA atomic. It executes on the wire and in the NIC very much like an RDMA read. It's ordered, it's flow controlled, it's acknowledged, right? Just like an RDMA read. You have strong guarantees about how it behaves with respect to RDMA writes with other RDMA reads. And it's acknowledged. You send a request, you get a response, right? With RDMA write, you get a transport ACK, but you don't get an RDMA ACK. There's no such thing. So this is an explicit operation, bidirectional. All prior writes on a Q pair are guaranteed to have pushed, just like with an RDMA read, prior to executing the flush. The flush actually has to wait a little longer than a read does, but than an RDMA read does. But it executes in a similar way with respect to RDMA write. In IB and RoCE, that's called a non-posted operation. It's something which is not posted directly to the PCI bus. It's sent to a queue first. iWARP explicitly calls that queued. So it sits on the queue till it's ready to execute, then it executes, then it produces a response. The requester specifies a byte range, one or more ranges, to be made durable. It says, this memory handle, this offset, and this length. Please make those bytes durable. The responder responds by guaranteeing that that specified range has been made durable, persistent. It may flush additional data. Some responders are forced to flush everything. They have no idea what to do. They're just going to flush the entire bus complex. Others might flush a page or extra cache lines or whatever, but they may do more work. It may have already been flushed, so there may be nothing at all for the provider to do at this point but respond. But in any event, that's an implementation question. The minimum guarantee is the protocol says, I told you to flush bytes 5 through 10. You flushed bytes 5 through 10. Yes? Yes. Done. Good. So the single flush may act on many prior writes. You can do write flush, or you can do write flush, write flush, write flush. You can do whatever you like. The responder acknowledges only when it completes. However, the connection breaks if an error occurs, right? And we do that to preserve RDMA semantics. We could return status, but there was a lot of discussion in the various groups about this. And it was decided that the status is A, very hard to generate, and B, rather meaningless. The application really can't do anything in particular with the status. It just needs to know that it's flush failed. And then it needs to mop up, because the error case is really quite complex. There's no way that a simple status could ever reflect that complexity. So, like it works with RDMA read or even RDMA write today, if you couldn't do what I told you, break the connection. So that's how it behaves. It sends back a syndrome bit that says, flush failed. But that's pretty much all you get. So here's a little picture. This is a picture from the application. We start with the application on the left and we move to the right. The application has done a bunch of work, not shown. It then says, I want to flush the contents of memory, so I call optimized flush. This is the original optimized flush version, which proceeds to flush, flush, flush by doing write, 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 followed by flush. And you can see that there are RDMA writes on the wire, PCI writes in the host, and something hits persistent memory on the right. And so there are 3 little tricky bits labeled 1, 2, and 3. The RDMA writes completed really early, right? They didn't really mean much. They were a transport ACK. Maybe they were even a local ACK. It doesn't matter. But they mean nothing. So RDMA write completion didn't tell anybody anything useful. Number 2, the remote flush appeared before all the RDMA writes appeared. Number 2 actually ought to be a little bit to the left. You see how the flush appeared prior to the last write being issued on the bus? So the flush had to wait a little bit, and it had to make sure that all those prior writes were done before it responded. And so there's a couple little bubbles in that picture, right? Async flush helps get around the bubbles. The first is, I'm going to take my time here, you know, my full deadline scheduling. The application can do overlap processing, and that's shown here. You can see now we explicitly call out stores to memory, followed by this animal called async flush that's invoking the library. And the only thing the library does is launch a few RDMA writes that map to the addresses that were flushed. And it just returns immediately. We actually take, you know, good advantage that nothing blocked here. All we did was we fired off a bunch of RDMA writes. And they all happened asynchronously, right? The network got busy, the remote house bus got busy, the remote persistent memory got busy. Everybody but us is busy, right? We're done. So we go back to work. The application goes and does some more processing, creates some more stores, flushes those stores, and then all of a sudden the application gets to a point where it says, okay, I got to commit this. I have to make it persistent. So it calls async drain. And async drain is the bigger hammer that then invokes this thing called RDMA flush, remote flush. And that flush does the exact same thing we saw in the previous picture. It waits for all the prior writes, et cetera, et cetera. But you see we got a lot of work done, and we shifted that whole diagram down so that we were able to overlap a lot of processing. So we're much more efficient. The subtlety I mentioned earlier is that drain means we did a write, and flush means we did flush means we did a write, and drain means we did a flush. So our language is a little odd, but forgive me for that, and we'll fix it over time. But the RDMA protocol was exactly the same as the previous. All we did by if you will, deconstructing the optimized flush is we made a local change on the initiator, on the requester. We're doing the same protocol, we're just making better use of the network. What else do we want to do? Well, the second option, the second workload on my little thing a couple slides back was transactions. We need a transactional write. We need the ability to perform some sort of atomic update using RDMA. That's not currently possible to memory, right? An atomic operates within the scope of a NIC, within the scope of a single NIC. That was done for a very good reason 15 years ago. There was no such thing as a PCI atomic operation. That's no longer the case, although it's not fully adopted. But in any event, we want to make sure that we have an operation that insists on this atomicity. We don't want to say, well, it's a side effect of atomicity that if I'm on a PCI atomic implementation, it'll be atomic. No, I don't want to find that out at the RDMA layer. I want to say, look, you're going to do this atomically or you're going to fail the operation. So we've added a new thing called a transactional write. We call it atomic write. And we constrained it in an interesting way so that it can run over a non-PCI Express atomic fabric. We can perform an aligned cache line sized write in an atomic fashion. Maybe not, but probably yes. Second thing we might want is an integrity check. As I mentioned, if we drop the data, how do we know it's good if there's no CPU to check it? The third is encryption, the ability to protect our data, both on the wire and at rest. I'm not going to talk about that quite as much. But anyway, we're discussing all three of those things. The first one is, however, already decided. There's a second new operation on the RDMA agenda called atomic write. It's a new non-posted or queued operation that executes at the responder only after successful prior non-posted operations. And the one we're really interested in here is flush. So the idea is we can implement a log writer, right? We can write a block of data, commit it to persistence, update the pointer. And we only update the pointer if it was made persistent, right? We can't possibly update that pointer until persistence is guaranteed. Log writers break when you do that, right? So we implement an atomic write. And our picture here is over on the right. And for some reason, the animation isn't working. Darn it, whoever loaded this didn't enable animations. Anyway, it very nicely shows each step of the way here. where the application calls put followed by flush, and the flush goes off and executes. And then immediately afterward, he does this atomic write pointer update. And the atomic write hits that stop sign and waits for the flush. And that little green arrow that comes out of the flush down to the stop sign lets him go. And once he goes, he performs his write, and boom, he can respond. And so this very simple operation looks just like any other atomic, but it has a couple of very specific guarantees associated with it. Allows us to implement a log writer. What if the log writer is paranoid? What if the log writer said, I want to write the data, but I don't want to say it's good until I verify that the data was written successfully. Here we have a new operation that is not yet decided. However, I'm pretty sure we need it pretty much the way I'm specifying it, so I'm just going to shove it down everybody's throat here. This is Tom Talpey's idea, but it's not necessarily the decided on idea. So bear with me. In any event, here, after the flush, instead of doing a write, we follow it with a verify. The verify has the same queued behavior. It gets on the queue, it stops at the stop sign, it waits for the flush. Once the flush occurs, it verifies. It reads the actual physical media, computes a hash, compares it to a hash that we expected that media to have. If it succeeds, we turn on the green light and we respond verify complete. If it fails, one of two operations occurs. One is we say we return the bad data, we return the hash, but we therefore signal that it's bad. Or second, we stop. We break the connection right there. And that's really useful for the paranoid log writer because that means we would not update the pointer. But by returning the hash, we support a scrub. We could say, I want to connect and I want to look at every block and I want to make sure that the block matches what I think the block should have. And so I can just keep reading it. You're not going to break the connection every time you find a bad block, right? You're just going to tell me what blocks are good and what blocks are bad. So for recovery or scrub or adding a new device, that type of thing, we can support both those semantics with a simple yes/no option bit saying break the connection if it didn't match. There have been some alternatives proposed. I'll mention a proposal by Adnan Burstein in which they do SCSI T10 diff, which I personally disagree with, but I won't take the stand on that right now. I will mention, however, that even with these 2 or possibly 3 RDMA extensions, there still is a role for an upper layer. RDMA doesn't become a storage protocol with these extensions, nor do we want it to become a storage protocol. We want RDMA to become an offload for the data handling to persistent memory. We want the storage protocol to continue to do everything it does. Connection management, authentication, right? Who the hell are you? Why should I give you permission? Okay, am I allowed to give you permission? Authorization. QoS, you're jamming all this data down my throat. How do I know you're playing nice? That kind of thing. All the things that upper layers already do. So we want upper layers here. We just want upper layers that are RDMA aware to be able to optimize the persistent memory flavor of their client's access. And so this is something that I've talked about in SNIA a lot before. In fact, I mentioned it 3 years ago here, so I'm not going to mention it again. But don't forget, there's always going to be an upper layer, in my opinion. We're not going to do raw RDMA storage here. Maybe some applications can do it. They're still going to talk to their peer. They're not just going to discover PMEM out of nowhere and make connections to it and start using it and partying on. There's always an upper layer. Don't forget, we're only optimizing the very bottom of the data path, the hot path, what RDMA does best. Wrapping up, there are some standards efforts around this. There are 3 in particular that I want to call out. The first is the IETF, which you probably haven't seen much activity out of because the contributors have been running it in other ways. But the IETF owns the iWARP spec, and 3 years ago I published an RDMA commit draft. The URL is down there in the 3rd bullet. It's an individual draft. It was for comment. It generated comment. There are a lot of updates to that draft sitting on my laptop, and I intend to publish them soon with some new co-authors. But most of the ideas I described in the slide are in great detail for the iWARP protocol in that document. The second group that's working on this is the IBTA, the InfiniBand RoCE effort. And LWG took up this effort in mid to late 2016. I've been participating in that effort. In fact, we've been pretty much driving a lot of the discussion in IBTA, although I've driven the discussion in other ways as well. It is intended to become a new annex to the core InfiniBand spec. It is not yet publicly available. It's still going through the LWG process. It was described last month, actually in January, 2 months ago, at the Persistent Memory Summit by Adon Burstein. The URL is right there. You'll recognize some of the slides that I use here. Some of them Adon and I both used from the SNIA discussion. But it describes, in a somewhat more authoritative, from an IBTA perspective, statement of the plan, and also discusses some of the integrity and security counterproposals that are floating around. They're all valid, and this discussion has been really, really valuable. It's good because, if I just go off track a little bit, the persistent memory roadmap has taken a while. It's still unfolding, right? Persistent memory is still not a reality in volume in the market. And I think that's good in a way, because it has allowed us to sit back and think and to get things right. And with protocols, you really want to get things right. You don't want to hack in a protocol. You don't want to just deliver some half-assed thing that you have to fix, because now you've got a legacy problem. When you ship a protocol, things are going to speak that protocol forever, right? It's not like you can say, upgrade your protocol. No, there are some machines that won't upgrade, and you still have to talk to them. So if you launched an RDMA read to perform a flush, I'm sorry, you're going to regret that someday. You want a flush to perform a flush. That's my strong opinion. Anyway, I just wanted to say that the IETF and the IBTA efforts are in harmony on the flush semantics. These aren't disagreeing with one another. The idea is that there will be a common verb layer for these semantics, but a different implementation on the wire, which is natural, and I think a good thing. There's a third standards group that I don't have a lot of visibility into, but it's very desirable to have PCI semantics. These NICs plug into PCI buses. There's no way to perform a flush over PCI today. So we would like to see the similar extension in the PCI specification. My understanding is that the PCI SIG is discussing this, but the PCI SIG doesn't, what happens in the PCI SIG stays in the PCI SIG until the PCI SIG is good and ready to open the door. So I don't know what the heck it is, but everybody gets all coy with me and won't tell me what's going on. Sorry. But I will point out that back in August of 2017, there was published by the PCI SIG a so-called Atomic Operations ECN, Engineering Change Notice. It's not an errata, it's a notice. It's an update, if you will, an optional section updated. And there is an atomic operation in PCI today, just a couple years old. And it's also my understanding that some Intel PCI root chipsets are speaking this atomic now. So I have hope that NICs will begin to use this, to take advantage of this new operation. Anyway, those are sort of the big three. Obviously, there are middleware standards, open source standards, upper layer standards, you name it. But these are the ones that we're working right now. Finally, next steps. The NVM programming twig will continue to work on the specification. We welcome and await OFIWIG feedback on these semantics. We'll work together to get them right. IBTA and IETF RDMA standards will proceed, and I hope that they will reach maturity in the course of time, right? You can't predict how standards efforts proceed schedule-wise, but everybody's very motivated for this. OFIWIG and RDMA software implementations, I believe, need to move forward. We're pretty much ready for this. I think we know what the verbs will look like. I don't see any reason why we shouldn't start implementing them, at least as a verb method. Maybe not plumb them all the way through until the protocol's done, but we can get started on that. Open source, commercial OSs, you name it. RDMA vendors should begin to build this. I know they are. The PCI SIG should produce a flush, and we'll be a whole lot better off. Questions? Sure. Oh, Gen Z. Good one. There is. There is. Gen Z is a much more exciting fabric than PCI Express, right? And OpenCAPI in particular. There are some new hardware motherboard interconnects which are extremely well adaptable to persistent memory requirements, right? They can put persistent memory outside the box. They can put persistent memory inside the box and handle it in very different ways. They can allow I/O devices to access it as a full peer. They don't have to go through some skinny little PCI route. There are quite a few people very interested in the implications of remote persistent memory over those types of new motherboard interconnects. Yeah, I can't speak for them, but they did speak at the Persistent Memory Summit last month, and they also spoke last year in the last 2 January PM summits. I can point you at their presentations, and they talked about some of these implications.
Why is T10 diff not?
T10 diff was a solution for 512 block sectors on spinning rusty media. You know, it works great, and it goes through firmware that might put the block you wanted at the wrong LBA and things like that. You need to find those problems out. So it took a little, 8-byte blob, and it appended it to the data and stored it with the data. The problem is the 8-byte blob has things like an LBA number, a sector size, wired into it. It has a 16-bit CRC, a very poor CRC. None of this is matched to an arbitrary byte addressable terabyte-sized memory array. And so if you did use T10 diff, you'd be rewriting the thing constantly. Every time you updated a byte, you'd have to update the T10 diff. And that means that the initiator would need to know the original integrity and recompute it, which is entirely the opposite of what you want integrity checking to be. So I just think it's an incredibly bad match to the capabilities of persistent memory. To say nothing of a 16-bit CRC, which is just hopeless. I mean, it starts at a 32-bit CRC. It goes up to a 64-bit or SHA-512, really. That's what you want.
I mean, there is the application tag piece of it that could be extended, and maybe there are different modes for,
You still have a limited amount of storage and a block semantic. I'm sorry, but I don't think it gets you past the starting line to overload the other extendable stuff. Yeah, my opinion. It's fine. I've said this before. I've done a lot of thinking about it, obviously. It's totally fine. You don't have a question. Thank you.